Alrighty. Um, so today I'm going to be going over a paper titled Stabilized Medical Image Attacks. It was published in March of 2021 in the ICLR conference. The high-level goal of this paper is to give computer vision engineers, particularly those studying the medical images, a way to efficiently create robust perturbations to test their model on a variety of tasks. Emphasis on robustness, and I'll explain more on that when I get into the paper. So earlier in the semester, Dr. Chen went over adversarial attacks, so I'll just do a quick review using one of the images I liked from his presentation. It was lecture 12 for reference. So given some image of a macaw, we as humans can clearly see it's a macaw, and a neural network that's decent should be able to identify it as well. However, with adversarial attacks, we add a little perturbation where we adjust the values of each pixel ever so slightly. And while the image looks the same to the human eye, neural networks are confused because these perturbations are meant to maximize the deviation between the expected ground truth and what actually gets output. There are two types of ways to generate these perturbations. One way is the white box attack, where we have complete knowledge of the architecture and the parameters. The other is the black box, where think about if you send an image off to the internet and they spit back a classification result. This would be a black box because we don't know what the architecture is. Today, we're going to be looking at this approach we're going to be studying today uses the white box, so it does have knowledge of parameters and the architecture of the CNN. So why do we care about adversarial attacks? Well, due to the sheer magnitude of the medical economy, the authors believe that attackers would look to manipulate medical records and potentially do insurance fraud for their own profit. Another reason is that data loss and noise is an unavoidable part of the data collection process in medical imaging, and that itself can produce perturbations which could trick the model. These misdiagnoses can result in more expensive and lower quality healthcare for everyone, so it's important for model architects to ensure their models are robust to such perturbations. However, generating perturbations to test our models is difficult for medical imaging, as many of the current techniques have focused on the natural imaging domain. One such prior work is the FGSM model, which is where we have some input image that's going into a model. Here we have a panda. So to create a perturbation, we simply take the gradient with respect to the input of the model. Typically, we would do the parameters if we wanted to improve the model. Here we're doing the input. We only care about the sign. And basically what the sign tells us is by decreasing the value of a pixel, we can make the model worse. Or if it's negative, we can make it worse by decreasing the value. If it's positive, we can make the prediction worse by increasing the value. And then we multiply all these signs by a small epsilon, and this ensures that our changes are small. And then by adding these values to our original image that we have, we can get a perturbation, which, since all these offsets were meant to confuse the model, we now have a model. The model is now unable to accurately classify the image. There do exist slightly different methods for adversarial attacks besides FGSM, but this is one of the most famous and is the basis for this paper. In the medical imaging field, there are many tasks that we have to perform on different types of images. The authors of this paper provide a few that I will go over, such as classification of severity using fundus images. Another one is segmentation of lungs for COVID dataset. Another task might be object detection. Here they're using endoscopic images. And you can see that this is some of the previous works, FGSM. you can see that the grade has been incorrectly identified here. The segmentation of the lungs is poor, but you can still see some of the left and some of the right is still accurately segmented. And here the artifact is still present. The new method, however, performs each of these tasks with greater success than previous models. Here you can see the grade 2, which is better than either the other perturbations. This one's kind of funny where it segments everything as a lung except for the actual lungs. And then lastly, even on the object detection, it shows great success with confusing the model. So typically what happens is with the FGSM is we just care about how different a proposed perturbation is from the original image. So we would simply take the derivative with respect to x, or respect to the input, and get the gradients. This would give us our perturbation, which we would then apply to our model and update the input. And this would be an iterative process, so we get better and better perturbations. However, the authors of this paper realize that this process just is very locally minded. We're trying to select perturbations that are the best with no context to what might happen if noise or modification gets applied to that perturbation. So if, for example, you have a really good perturbation here that confuses the model into thinking that this car is a turtle. But because you've never modified that perturbation, if any kind of noise, such as some kind of Gaussian smoothing, gets applied to that image, that perturbation might just go back to guessing the original image or the original label. So it's important, if we want to make good perturbations, we also need some context. We need to test our perturbation after it's been smoothed or after noise has been applied. And that's kind of the idea that inspired this paper for the authors. So here, so if our goal is to trick the model, a simple idea would be, instead of just making a perturbation based on how it deviates from the ground truth, we also look at what the model predicts after the perturbation gets modified. So here you can see this would be a bad perturbation because after it gets modified, it's not guessing, the model is no longer guessing the same wrong answer. So this means the new loss value for this stabilized medical image attack approach will be the deviation term plus a stabilization term multiplied by some alpha. And this alpha is just how much emphasis we want to place onto the perturbation being stable. So here we have our original deviation term, which is just how much the perturbation differs from the ground truth. But we also have a stabilization term, which we would like to minimize. So to minimize this, we want the prediction of the models to be identical before and after the perturbation gets modified. So this combination of deviation and stabilization forces the perturbation to be robust to modifications such as Gaussian smoothing. This whole idea is basically the whole paper. The rest of the paper kind of will talk about the mathematical backing behind their method and experiments to support it. But this idea of being robust to smoothing and noise with our perturbations is the whole idea of the paper. So now we'll analyze the stabilized method from the perspective of KL divergent, which is just a way to quantify how different two distributions are. Here we want to measure how different the distributions are for the perturbation before and after modification. So we'll let y represent the different states that our model could output, and p will represent the probability of getting some class y when we put an input x into our model. So we can get our two probability distributions, one for our augmented image, and then one for our augmented image after some modifications happen to it, so such as Gaussian smoothing. So here, eta prime is just how much each pixel and our augmentation changes after it's gone through Gaussian smoothing. So if you wanted to see what the difference between these two distributions are, an easy way to do it would just be subtracting these probabilities. However, since these probabilities are close to 0, and you might get some value close to 0 if you subtract them. So doing some log probabilities, finding the log of each probability will convert it to a more reasonable number, and we can do some log manipulation and represent them as dividing each other. And since there are multiple classes, we want to know what the average difference between these two distributions are, and we can represent that using the expected value. So the KL divergence of these two is just the expected difference between the probability of the original perturbation and the probability after the perturbation has been modified. So the goal of the stabilization term is to make these two probabilities as close as possible, which would minimize their divergence. So we can rewrite this term using the second order Taylor expansion. This math isn't too important. So this term here represents the Fisher information matrix, which we can write in a more intuitive form as the following. You can see there's about a page of explanation on how to convert this in the paper, but that's not very important to the understanding. Essentially what this is saying is 1 over the probability of getting each class for every possible class, and we want to sum that up. So when we plug this back in to our stabilization term, we get the following equation. And this gives us a lot more insight into what the stabilization term is actually doing. So first off, we have this summation. If we want to minimize this summation such that all the probabilities have to add up to 1, the best way to do that is for all the probabilities to be the same, 1 over k, the number of classes. This means that this term is trying to force all the probabilities to be equal for all the possible states it can be. This is a fixed spot that our stabilization term is trying to get our perturbation going towards. So one of the key takeaways from this paper is that it's forcing the perturbation to move in a constant direction. It has an objective goal, and that goal is this spot. The second term, which is eta, how much each pixel is being modified after it in the augmented image, we want to minimize this term. So if our eta, our augmentation, says, hey, let's make 1 pixel really bright, and that confuses the model really well. Well, this is bad because if we apply Gaussian smoothing to such offsets, we end up with large values for eta prime after we've smoothed it. A better version of this with a smaller variance would be something like this, where the values are closer to each other. And when we apply Gaussian smoothing, values change by smaller amounts. So looking at the good and bad examples, if we were to multiply the good example by itself, we get a much smaller value than if we multiply the larger values by the bad example to itself. So these two terms are trying to minimize the variance in eta. So the ideal, we don't want to put such great emphasis on a single pixel. We want to modify essentially all pixels by a little bit instead of 1 pixel by a lot. That results in much more consistent perturbations. So summary, the first part of the stabilization term is making sure we're heading towards an objective location, and the second term is minimizing the variance of our perturbation, eta, which results in much more stable results. As a visualization, if we were just using the deviation term, which is FGSM method, we can see that the variance is very high. It goes from 62 down to 2, back up to 54. However, by adding stabilization, our variance is much more consistent. Another thing to note is the cosine distance. If we treated this perturbation as a vector, we can see that we're taking a step in one direction, and when the cosine distance is negative, that means we're somewhat doubling back on ourselves. So it found a good example over here with the first iteration, but then it realized a few iterations later, wait, the best perturbation was back the way we came. So it's a little bit unstable, it's bouncing around. Meanwhile, with the stabilization term, we're always moving in the same direction. It has a fixed destination it's kind of heading towards. So as an example, if this is the perturbation space, deviation is kind of doubling back on itself, going back and forth. Meanwhile, adding the stabilization term makes it go in a much more constant direction, which results in faster convergence. The authors performed a ablation study where they compared deviation and deviation plus the stabilization term. The clean method is just the input using the ResNet 50 with no augmentation. So using the stabilization term, we get worse performance, which is what we're trying to do. We're trying to trick the model for lung segmentation on the COVID-19 dataset. We also see that our cosine percentage, which is the percentage of positive cosine values we get, is much higher, which means we're more often heading in the same direction, or more often moving in towards that fixed destination, which is why the stabilization term results in faster convergence. We can also see that in artifact detection, object detection, we get better results using the stabilization term, and same thing for classification task. We get better results and still higher cosine values. For the number of iterations, they compare the number of iterations it takes to perform well. So DAG, which is another adversarial attack method, that's state of the art. At 15 iterations of performing both, SMIA is much better. They go up to 20 and 25, and it still is performing better. Eventually, it converges to around 0, so DAG does catch up. Just for reference, DAG usually takes like a maximum of 150 to 200 iterations, so it converges much faster. And then some comparison to the state-of-the-art models. On the COVID-19 segment data set, the stabilization term performs much better. You can also notice that the perturbation variance, so the variation between the perturbation created is much, much lower using the stabilization term, because that's what it's trying to focus on. So what that means is if some kind of smoothing or noise gets applied, we can expect the perturbations created from the stabilized method to be much better than the other perturbations. On the AED data set, you can see similar. The DAG does beat it out. And then another benefit is that DAG is unable to perform classification task, so they had to use a different method, DeepFool. Meanwhile, the stabilized method is able to perform all different kinds of tasks. So over here, we still have another classification task, and it's still performing state-of-the-art. The authors do show a natural image. I guess their version of a natural image application of this through the MNIST dataset, and it does perform better than other adversarial attack methods. It does seem a little weird that their natural image application, they chose to use MNIST instead of, say, ImageNet or some other more popular data set, but this is what they did. And that's about it for the paper. The paper overall, the code for it is very, very simple. It's simply one stabilization term. The GitHub for it is only 90 lines of code, making it easy to add to any other adversarial network. And I do think that adding stabilization terms to other adversarial networks or adversarial attack methods could show some benefits, since all this paper is trying to do is stabilize the method to modifications. So the perturbation has more global context than just like some local selection. The paper shows a lot of good theoretical backing. So it does have some weaknesses though. It does fail to thoroughly test the model on natural images. It only uses, even though it's focused on medical imaging attack, I do think this method could help with natural image attacks, and it could have at least shown some better comparisons. And one of the advantages of DAG is that its perturbations can be applied to other images with great success, making it a very good black box attack method. The authors of this paper show no attempt to test the transferability of their perturbations, and I think that would have been a good insight for those reading. And yeah, that concludes my presentation.
Okay, yeah, thank you, Jacob. I think you did a great job explaining the math behind the method. So definitely there is a lot of, mathematical derivation and, prove to back up the theory of the method. So yeah, I have a couple of questions, but before I want to see if the student have any questions, so they can ask first. Okay, do you guys have any questions? So we want to have like very active engagement for the discussion. Anyone? Okay. So I think for the motivation of their approach, right, it's just to be more kind of doing more robust attack, right, for the machine learning model, because some of the pre-processing like Gaussian smoothing and maybe do some augmentation or maybe using some compression algorithm that is able to kind of mitigate those attack effect. So I was wondering, in their experiment, so they show these different attacking algorithm, right? FSGM, DAG, and their stabilization method. Are they also doing any, like using Gaussian smoothing to process the image and also then testing how robust, how successful is their attack method?
They do not talk too much about the pre-processing. They act, they don't elaborate very much on their experiments. They discuss which model they use once.
Yeah.
I think the experiment section could have been elaborated on because there are a lot of hyperparameters between all the models and different ways you can pre-process. So I think they were trying to be concise with it.
Yeah, but I'm just curious because they spend a lot of time to motivate, right? So if you go to like the very beginning of the slides, they mention if you do some Gaussian smoothing, right? So maybe some of the perturbation can be easily removed, right? So then the model is able to correctly classify or segment the object of interest. So they want to increase the robustness to this kind of smoothing, right? At least Gaussian smoothing is one of the pre-processing steps. They want to try to be more robust. So that's my question, like how do they evaluate the robustness, right? So are they, you can have the adding that perturbation and then directly evaluate the model, but do they also using Gaussian smoothing to process the attacked image and then apply the machine learning model and get the result? So I think that's the question, right? Because if they say they are more robust, then definitely need to show some experiment to validate this.
Yeah, it definitely seems like they focus more so just on like directly applying that image into their uh, model. I think the main goal, I guess, the main goal of this paper was more so to create perturbations that are better at tricking the model. Um, I think it being more robust is kind of a side effect of their approach.
Mm-hmm.
So they they don't really discuss pre-processing and doing the Gaussian smoothing. I think that's something that definitely seems useful in, to showing how robust it is, because I do believe
Yeah,
it is more robust. But no, they don't mention anything about that.
yeah. So I think it will be great to adding some result in addition to these tables. I mean, these are good result, standard result, do the comparison, but it will be also see how robust their attacking method is to different like defense mechanism, right? We can say Gaussian smoothing or maybe some compression or augmentation is sort of very straightforward or easy defense mechanism, right? So after applying that and see if they are still able to get a very successful rate to fooling the machine learning model. So I think that's one. I think one experiment seems to be missing. Definitely can further justify or validate how how good is their how robust is their method.
I also, since they reference using Gaussian smoothing, but if you're trying to make sure your perturbation is more robust, you really could use any kind of
Yeah,
modification here. You could add noise, you do Gaussian smoothing, or just some kind of anything else would also work. So I think maybe trying different versions of that could have also made a good experiment.
yeah, yeah. Because in the class we talk about a couple of like how can you combat with the adversarial attack, right? So these smoothing image smoothing is one particular very simple and easy to use method to kind of combat this kind of adversarial perturbation. So I think if they are specifically mentioned this point, then I think it will be worth to do some experiment and see if their method is really able to kind of counter this kind of smoothing effect. Yeah. Okay. Um, Another thing is you mentioned the other state of the art approach is DAG, right? When you say, yeah, there's a couple of iteration. Can you show that slide? Like they show the result for different, yeah, iterations. Um, so what does this mean like here? The
They're
attack
just
performance for different iteration numbers. Yeah, can you explain this?
yeah, so they're just saying so like when you're doing FGSM, you're adjusting how much you do multiple iterations to adjust like how much offset you put on each pixel to figure out like the best one. So they're running their algorithm. They're trying to show that their algorithm converges faster and gets better results because
Mhm.
they typically only run their algorithm around 25 times. Meanwhile, stuff like DAG takes 150 iterations. So they're just trying to show that they get better results faster.
I see. Okay. Yeah, I say if you have some budget, right, you can only perform maybe 5 or 10 iterations, then they have an advantage, right? Converge faster, right?
Yes.
Based on the result here. Okay, I see. Yeah. I was also wondering, like, because their method seems to be generic, right? And they were mostly applied to medical images, although they did MNIST. And you are right. I don't know, like why they are just choosing this very small digit image. Like a natural image will be like ImageNet, at least like a Sapphire 100 or Sapphire 200 will be much better to showcase if their method is going to be generalized to natural image as well. Um, yeah, I don't see there's any specific like element or recipe that is developed for medical imaging. Pretty much this is like a general method, right? So it's just adding a stabilization term.
Yeah. So I guess their main goal, like, since since medical imaging, like, there's very small pieces. Like, if you have a image of, wait, pull it if you have like lesion detection, you want to know how bad the like scars are, you're trying to rate it. A very small part of the image could result in very large differences in the grading. So there's a lot of variance with it. So the whole point of the stabilization essentially was to try and minimize the variation of the perturbation.
Mm.
So they didn't want it to be like, if you, yeah, I guess that's what they're trying to do for medical, make it suited for medical imaging, trying to minimize this variance.
Mhm. Okay. So for their method is basically adding extra term, right? So did they do any experiment maybe using adding this kind of reducing the variance to other approach, because it's just adding an extra term, right? So it can be considered as like a plug and play approach. If they can combine with like a DAG or maybe FGSM or Deep4.
Yeah, it really is. I mean, the whole paper is just like this one term that's just an addition. It,
Mhm.
because it's just a way of evaluating how robust a perturbation is that you're creating. So it could be applied to anything. That's one of the strengths of this, but one of the weaknesses of this paper is that they don't actually do that.
Yeah, yeah, it's kind of one strength, but also the weakness without actually demonstrating this point, right? And we can definitely claim this is a benefit. Plug and play can be combined to any method. But it will be better to do this kind of experiment and show that it can be readily applied to any existing attack algorithm and also able to make it more robust. I think that will be very valuable. Make this paper much stronger because that's one, definitely one, very good merit of this approach, right? So a lot of applications, people won't have this kind of very simple things. People can, take it and plug it into whatever the choice of their attack algorithm and make it even better. So I think that's very important. Yeah, it's a little bit shame they didn't do this kind of experimentation to kind of strengthen this point. Yeah. Okay. So you also mentioned are there a lot of parameters they have to tune? So here I see alpha is one. Do they have other parameters?
Uh, there's not a lot of parameters. All they're like alpha is a hyperparameter, so that's selected ahead of time. They don't tune that during the process.
Mm,
Um, I actually, where is it? Yeah, I didn't show this during the lecture, or
okay.
the presentation. But they tried different alpha values to see which one fits best, and they found that like an alpha value of 1 is good.
So do they have to tune this alpha value for different data set, or this is like a, you know, one time deal, like can be applied to different data set? Maybe I can put it in this way, how sensitive is this alpha parameter?
House, I don't. I I think like they don't elaborate it too much. They do a bunch of because they do like the COVID-19 data set, the EAD data set. They don't really elaborate on which alpha they use. So I think they just do something similar to like this, and they just find which alpha works best, and they just go with it.
Mhm.
Um, I think like here you can see um, it's pretty clear. Like it just around 1 is the best. It just decreases, then it increases again. So it's pretty easy to find the best
Mhm.
hyperparameter for alpha.
Yeah. Okay. Yeah. Yeah. I think this one is definitely want to see if have a very kind of wide range for this alpha, because if you have a very narrow range, then could it be something very brittle for their method? Because for each of the data set, you kind of have to carefully tune this alpha parameters to make it work, or to achieve the performance you want, right? But if you have a decent range, for this alpha, and more or less can achieve like similar performance, I think that'll be um, at least something people will prefer to use this kind of method. Rather, you have to carefully tune this parameter. Okay.
Yeah, I guess to counter that point, like alpha is basically the only parameter you have to tune.
Mhm.
So you can put all your focus on just like tuning one
Yeah.
parameter, and you don't have like 50 that you have to
Yeah.
juggle between.
Yeah. Okay. Yeah, I think this is good. Like one parameters, no big deal. If you have to be carefully tuned, that I think that's fine. So I think maybe I just want to make this point. For you guys, if you're doing some of the research, have to think about how complicated is your algorithm, right? If you have too many parameters, that can be easily a red flag for reviewers to attack your method, because um, unless you have like a universal set of parameters can work well for different data set. If you have to carefully tune like a set of parameters to work well for each of the individual data set, then that's going to be a problem. People wouldn't, even if you achieve the best performance on each individual data set, then one weakness people can still mention is that it's just too sensitive for your method to work well, in terms of these parameters. So that's something to think about, when you develop your own algorithm for your task. Okay. Okay, all right. So I think, yeah, this is a good paper. They have some interesting findings and seems to be a very easy things to do. Did you actually check their code, right?
Yeah, and it's like 90 lines.
Okay.
It's very
Yeah,
short.
yeah. I think that's great. So you take some time to actually look into the code to understand the whole how their implementation is. Okay, great. Okay, all right. Thank you again. We'll move on to the next presentation.
Thank you.
All right, thank you. Okay, Saras, I think you are the next.
Okay. So in this paper presentation, we will be looking over TAutoML, which is an machine learning based lesion segmentation. And this is also an automated process. This uses transformers. And this paper was published from NVIDIA Research and myself, Sarath, presenting this paper. So what is the primary motivations for this transformer-based automation learning? The first comes from, as you know, medical imaging is a key step in disease diagnostics and finding the appropriate area where there is a problem. And there comes a specific challenge in especially this lesion segmentation, where these medical images are taken with various modalities. This modality can be with the equipment that they are taking and with the algorithms that they are processing. They are highly changing and we need an automated method for that. And you also have seen that automation learning with neural architecture search has been explored in natural images, but it haven't been explored in the medical imaging domain. And also, as you know, modern transformers are able to solve the problems better in everything. We can see that these are the motivations to solve the problem. So if you formally define the problem statement, so you have to find a method to automatically estimate the components of a deep learning solution to perform lesion segmentation. So how do they do that? They propose to use a single vector called D, V. So this is a one-dimensional vector. This vector comprises of three components. So the A is one more one-dimensional vector. It's a neural architecture. Like you can specify how many number of blocks are there, what is the input feature to this. Sorry. What is the input to this neural architecture, and what is the augmentations that you should use for this model, and what are the hyperparameters. We will look into this detail in the next slides. So for this problem, the main thing is you have to find a vector V so that it represents all the components of the deep learning solution. And with that, you can perform lesion segmentation. So a little background about this problem in the area of lesion segmentation. First of all, in early traditional computer vision algorithms were used, and also later machine learning based algorithms were developed. These two types are dependent on the handcrafted models. If we handcrafted features. So if the features are good, this models is going to perform better. But if the features are bad, you're not going to get optimal results. And later we have deep learning based solutions. But in deep learning, you have networks designed for other tasks. Let's say UNet is there, but you try to use UNet on the current task. Like, so there is no specific network for a particular task. That's what they mean to say. And if you come to the use of convolution neural nets on medical imaging, as we know, UNets and its variants are used. As you know, that the variants can be like UNet plus plus and then UNet. These from such variants, we came to know that dense connections among the convolution blocks will be helpful, but you cannot say in no network has found out the optimal dense connection. So they try to use auto machine learning and auto deep learning for this technique. If you see the background in this area too, this was like primarily based on reinforcement based learning, and you will have a predictor model here, which initially guesses whether the architecture that you are thinking will give an optimal results will actually give some results or not. So this is a predictor model. And moreover, these predictor models up to now have been optimizing only few components in the one-dimensional vector field. So let's say they are optimizing only the convolution architecture. They are not optimizing the augmentations and the various loss functions. So this paper aims to solve this one by proposing an end-to-end automated solution. Okay, let's see what is their approach. So their approach will be like to create a large one-dimensional vector. This is able to represent the neural architecture, and this is the components. Okay, this is the main thing that in their solution, and they are using a transformers-based approach for the predictor network. So you have a handful of V vectors, and you pass them through a predictor network, and this predictor network ranks them among these V vectors, like which configurations is going to give like better accuracy. And from this, they take the top vectors and they test on the task at hand, and they will get the they will get the optimal network architecture and everything. So let's see like how they are encoding each thing into these three different vectors. So A is like network architecture. Generally, as for segmentations, we use encoder decoder based architectures, and commonly used architectures are UNets and variants. And these are densely connected, but not like randomly connected. This paper inspires from this one. It's a SpineNet, and this is an object detection framework. In the SpineNet, what happens is that these dense connections between each blocks in the neural networks are completely random, and the feature sizes between each block is completely random. Suppose if you take a UNet, in the encoder, the features are going to decrease, and in the feature size are going to decrease, and in the decoder part, features are going to increase. So in this SpineNet, that encoder part and decoder part will have random increase and decrease in the feature sizes between each block. And let's say, like as I said, like A is a vector, like it consists of 5 values, like the block ID and what are the operations that you should perform. You can say like match normalization and the choice of activation functions, and the spatial resolution level, like what is the resolution it is going to output, and also you are going to take 2 IDs of its predecessors. So a block can take input from 2 previous blocks. So that's why they mean the predecessors. So you encode these in the form of numbers into the A vector. So the possible possible types of blocks can be residual blocks or bottleneck blocks, or even you can use an axial attention block. And n such boxes in a whole network can be used. Now, if you can go over the choice of augmentations that you can have in a one-dimensional vector, It can be, you can choose at most n out of m augmentation. So let's say the vector is 2-dimensional. In the first cell, you can say like random crop, and in the second cell, you can say like horizontal flip. So these are the, so m such augmentations will be there, and you fill in the n-dimensional vector. Okay, and the choice of hyperparameters, the loss functions, you choose either dice, cross entropy, or a combinations of both. Optimizers, you can choose Andom, Adam, or the following. Also, you choose choice of learning rate between these two. This is a polynomial learning rate or constant learning. So learning rate schedulers, which means that after some specific number of epochs, you reduce the learning rate based on a polynomial function or a constant function. Okay. So this is the main core thing in the paper, which is a neural predictor architecture. So this architecture takes two vectors. Okay, takes two vectors V1 and V2, and generally ranks whether using architecture V1 gives better accuracy or architecture V2 gives better accuracy. This relation prediction vector is based on a transformer model, and it uses like fully connected layers for the binary prediction. Let's say like if you are getting from this vector, you are getting accuracy A, accuracy 1, it compares and it gives like binary relation vector. In order to train such a network, so what are the ground truths for that? So in the data set, you will have V1, V2, and their corresponding accuracies on a particular trained network on the data set. Okay, with you will have, suppose with this network, you are having, you train this on the data set and you get the accuracy. And if, since this is a binary comparison, you compare both accuracies and you will have ground truth 1 and ground truth 0 accordingly. After that, with this method, they try to prove their experiments, and they were using LITS data set. They were primarily using this because this data set is having large variance in quality and also in field of view of the data set. And basically, this is a benchmark data set for lesion segmentation. Others also try to claim that the architectures that are proposed optimal for this data set can also be transferred to other lesion segmentation data sets. And they use medical segmentation decathlon to prove the transferability of their method. So this is the network on the LITS data set after like running through the neural binary prediction network and getting the results. Here they are using this choice of augmentations, and this is the learning rate. They are using constant learning rate scheduler and the following loss functions. So this is their network that they see which is optimal for this LITS data set. If you see, there is like feature maps from different resolutions are passed to the next layers. If this, for this block, the inputs can come from the previous block, or also it can come also from its to its predecessor. Basically, that after getting these feature maps, they try to upsample or downsample before they pass into this block. And as you can see, the output, the architecture that they got is like completely asymmetric. You cannot, it's not like a traditional unit, like the kind of script connections will be between encoder and this parallel decoder. Here, it's completely random. And if you see the results on the data set, this one has almost overcome over the NN unit and U3 net and also like dense unit. So you can see like on the lesion segmentation, their dice score is 0, this following value, and liver on the following value. As you can see, almost on every other connection in any other network, they are having very good results here. And on the transfer data set on MSD, like this is the lesion segmentation also, they got this following results. This has beat this following methods, and also these variations in scores is also very less here compared to others. This is one more metric called NSD. It is called normalized surface distance. So the higher, the better for the score too. So it is also like very much high for this method. And these are the qualitative results of their method on the data set. As you can see, this is a 2D and this is the corresponding 3D rendered image, 3D rendered segmentation mask using graphics. Okay. And so coming to the main ablation study, they performed only one ablation study. That is, what is the choice of predictor architecture? As you have seen before, they pass two vectors and try to see which one performs better through a binary relation. So generally they tried out like linear relations like these functions. Okay, but they have found out that a transformer based architecture is giving good results. Is if you see, this is the ground truth rank and this is the predicted rank through the relation network. We expect this curve to be very straight so that the ranks are optimally predicted based upon the given network architecture. This is the line that they have got here. Okay. Coming to the conclusion, this paper implements a novel transformer-based auto machine learning method so that it can optimize every parameter in the deep learning network. And also, they are inspiring from this SpineNet, which is based on natural images. Finally, this binary relation prediction is like something new that they have used earlier. These predictors were just used to predict the accuracy, but here in this predictor, they are just predicting a relation between them, which enables them to rank better. And they are getting state-of-the-art performance on the following datasets such as LITS and MSD. And they also proven that their method is transferable to other tasks and datasets. And in the future work, the paper proposes like they have to reduce the search time for the network and also to reduce the predictor training time. Coming to the strengths of this paper, it's like a relation predictor model, and they are using transformers in 3D segmentation. And they are also able to prove that one network can be transferred to other data sets without any fine tuning. But the main drawback comes from their code. They are not having any code, but also the predictor architecture is not clear when they are proposing in the paper. They say that they are using a transformer network which uses transformer blocks and also fully connected layers to predict the network, but the attention and the dimensions that they're using to construct the transformer architecture, that is not clear here. And also they are giving only few experiments about transferability. They're transferring to one data set in MSD, but they are not transferring to other data sets and showing their results. Overall, I will give this paper 3 out of 5. Yeah, that's it.
Okay. Yeah. Thank you, Saurabh. Yeah. Maybe you can reshare the slides.
Yeah.
Okay. Any questions from the student? I think this is one of the paper you guys reviewed, right?
Yes.
Yeah. So I think you guys should have some. Since you read this paper, reviewed it, you should have some questions or comments on this.
I have a question. So from my understanding, the way that this paper works is that it creates two different types of vectors that contain information about the parameters and then attempts to make an estimation or predict which one will have better performance, correct? And so it's essentially just like a binary classifier, choosing one of these two architectures to use for a specific task. Am I correct in that assumption, or?
Yeah. So basically they have these ground truths for every vector. And in this one, they just use this transformer architecture as a binary, as a classification problem rather than the regression problem.
Okay. And so do these vectors evolve over time, or is it like how?
Yeah.
Okay.
There is a big search space that you can suppose. Just a minute. So suppose there is a big search space that you can choose V1, V2, V3 from. So they take from this one and they sample like, let's say 200, and they have the ground truths for this 200, and they train this relation predictor model.
Okay.
Yeah.
And let me think. So what exactly are the specific problems with medical imaging for neural architecture search that are different from other ones? Is it just that there hasn't been a lot of like focus in this field specifically for it, or a lot of attention, or is it the specific tasks are wholly unique for medical imaging when compared to other domains?
Yeah.
Is that
So,
question?
yeah, I got the question. So in this paper, when they mentioned that the challenges why they need automated segmentation is that while taking these CT and MRI images, there is some problem with getting these data sets. Like there are, due to the various imaging patterns related to the pathologies and scanning protocols and the medical devices that they use. So it is like difficult for every particular pattern to train a model and find optimal architecture. So that's why they propose to use some automated machine learning. And coming back to the, is there any background work in the automated machine learning in the medical domain? Currently, as they said, it is there, but they are not fully optimizing every parameter in the network. Let's say they are optimizing only A part, but they are not optimizing F and H part. So that's why they are motivated to solve this one.
Okay, got it. Thank you.
I
Okay.
have one comment.
Yeah.
Okay, rather than a question. So I was wondering, like, I see that in the tables, the improvement is not a lot when compared to UNet++ and NIUNet. So do you think that the computational cost or like the training time would like worth it just to make sure that like it's really applicable in real world or not?
Yeah. So they have a comment about what is the training time for their method. They say that this neural architecture search, initially, as I said, they will sample from a search space and they get the ground truth accuracies for each vector. And they say that is only the training time, that is only the time where that is only the place where it will take more time. But once you get this data set trained, the neural predictor can even be run on a CPU. That's what they say. So this predictor network, they say that it can be run on a CPU and it will take very less time to train. So they claim that it is like real world usable. But the thing is that they did not have any code so that we can reproduce what and confirm what they are saying.
Okay, gotcha. Thank you so much.
Okay, any other questions?
I could ask one. So, and this might be silly, but it was fun to think about. With the predictor, are there any augmentations you can apply to the input for the predictor itself, or does any augmentation immediately like invalidate the predicted output? Augmentations on the vector that's being passed to the relation predictor, to each of them rather, or any of them, any combination, any augmentation at all.
Yeah, if you are trying to augment it here, but that's what you are essentially doing is you are picking a new sample from the search space, right?
Yeah, basically.
So that does not make any difference. Like already you are picking the augmented version of a particular vector from the search space, and it is not necessary to make one more augmentation here, right?
It would be for training, but yes, I don't think it would make sense.
Yeah.
That's all.
Yeah. Thank you.
Okay, any other question, comments, thoughts? Okay. So I think maybe I can give you guys some of the background about neural architecture search. So we witnessed like different generations of deep learning architecture, right? From AlexNet, VGG, ResNet, EfficientNet, etc. So even every generation of the network getting better and better with some novel designs, trying to push the state of the art. But eventually, people starting come to like a bottleneck, is not able to achieve significant breakthrough for the design. If you think about, these are still considered hand engineering architecture, right? Although we say deep learning learn these kind of feature representations and classification by itself, right, during the optimization. But the architecture is still designed by humans, right? We design these kind of different architectures. And so for this neural architecture search or auto machine learning is trying to basically, just like you play with Lego, right? You have these basic structure or building blocks, right? So in these, you have different operations, like for example, 3x3, 1x1, 5x5 convolutions. You have maximum pooling, you have skip connection, etc. Here, you may even throw in some multi-head self-attention, whatever, as your building blocks. And you can, using these basic building blocks to come up automatically, to form a lot of potential structures, right? Depending on how you connect, what kind of building blocks you use, how you connect with different operations in different layers, then you can essentially come up a lot of very different architectures. So then the task would be, how can we rank them, right, to figure out which architecture has the potential to achieve the best performance, right? So that's the ultimate goal, right? We want to finding, kind of exhaustive, do some exhaustive search to figure out which one give you the best performance. So in the search process, you're gonna have some maybe ranking, metrics to figure out, right? Either you can, each of the candidate network, you can train it and test on the validation set, and based on the accuracy to rank them, right? So if you have a 100 candidate network and you train them and test on the validation, and you see, okay, I'm going to pick maybe the top 10, to further build it or evolve around it, right? So there's a lot of research, trying to see how can we develop a very good ranking metric or efficient ranking metric is able to kind of select or screening all those candidate networks to pick those are useful or meaningful. So that's the idea of the neural architecture search. Of course, there's a lot of things you can play with, right? So as I mentioned, one of the challenges for this field is you need to spend a lot of compute resource and time to search that, to do the architecture search, right? So now there's a lot of research work has been focused on, can we do some training-free architecture search, right? Rather training all those candidate network, can we have some metric, come up with some metric without the training? I'm able to identify some of the candidate has the potential to be the finalist. You can remove some of the architectures that may not be useful or bad architecture. So that's one very active research area. And another is you can also adding, when you search these architectures, you can add in multiple constraints if you want, right? If you say, especially for medical imaging, right? So once we have the final search architecture, you want to train it and deploy it, do some inference, right? For medical imaging, not just the accuracy or performance going to be critical. Maybe the inference time is also going to be critical, right? So maybe the doctor relying on this kind of initial result very quickly and maybe do some correction or whatever to make the decision, generate the report for the patient, right? You cannot wait a long time to waiting for this initial result coming from the machine learning algorithm. So you can combine maybe the performance as well as the computation constraint, let's say the latency or the computation in terms of flops as the constraint, like a multi-objective optimization to figure out what is the best architecture that fits these different constraints. So if you guys are interested in doing some IoT applications, right, not just for medical imaging, maybe other IoT applications, if efficiency is also one very critical aspect, then if you are interested in applying AutoML, maybe you should consider this kind of multi-objective optimization in your search procedure. Okay, so yeah, I think a lot of industries also interested doing AutoML because like I mentioned, a lot of domain, a lot of applications, right? There may be, there's some unique challenges they want to solve, right? The existing hand-engineered architectures like ResNet, other network may not be the best choice for them, right? So they want to, using AutoML to find the best architecture fits their need, right? So let the machine learning algorithm to figure out which architecture gonna be best for their application. So that's why right now there's a lot of hypes or a lot of researches for AutoML, and they have a lot of practical applications. So I think, yeah, this is a very good area. Also has a lot of challenges, like one which I mentioned, right? How to have this kind of efficient search algorithm to figure out the best architecture to use. So those are very good areas. If you're interested, you can look into more, or even maybe think about, if you have some own applications, maybe using AutoML as a choice. Okay. Okay. Is there any other questions, comments, or things you want to discuss before we end? Okay. All right. Yeah, thank you again, Saras, for the presentation. Let me think I have a couple of things to mention before we end the lecture. So one is one quick reminder. So your project milestone report is due April 8th. Okay, so just you can build upon the your proposal, right? Some of you guys send me email about changing some of the parts, like deviate a little bit towards your original proposal. That's totally acceptable, because during the course of the project development, maybe you encounter some issues or you want to change something. That's totally fine, as long as you do not change like a totally different project. Small changes, deviations, or modifications, that will be totally fine. Okay, so you can basically put some of the progress you have achieved so far for this milestone report. So like I mentioned before, I just want to make sure you guys are, stay on the right track, right? You are able to get some initial implementation done, and you hit some of the milestones, right? You still have maybe a small portion left to finish in the next couple of weeks. Okay, so that's just a reminder for you. It's due April 8th. Okay. And for the, let's see. For the next, we still have, I think two presentations, two papers. And after that, we'll have one class to talk about the final project. For any other questions, then we'll go to the project presentation. So actually after this class, I will send you the sign-up sheet. So we plan to have 4 or 5 presentation each class, which I'll talk about some of the guidelines during this class. I know some of you haven't finished the project yet. That's totally fine. Don't feel like afraid to present in the first class. Even though you haven't finished, that's totally fine. I wouldn't grade this based on the completeness of the project. Right, so basically I just want to make sure you have the whole idea of the project, right? So just the problem statement, your own method, and some of the data set you're going to use, what do you achieve so far, and if you haven't complete yet, you can also present, right? What will be left to accomplish for the next couple of weeks. Okay, so this is basically how the remaining of the lecture will be structured. Okay. Okay. All right. So that's it. Do you guys have any other questions?
Like, isn't the project milestone too early to submit?
I'm sorry, what's your question?
I don't think this is a valid question to ask or not, but this project milestone, is it like too early, or before the presentation start, we can submit?
Yeah, the milestone is April 8th, right? So if you have that ready, yeah, if you want, you can submit right now. But just submit before April 8th.
Okay.
Yeah. Okay. Okay. All right. So yeah, if you guys don't have any questions, we're gonna end here. You guys have a wonderful weekend. Okay. I'll talk to you next week. Okay. Right. Bye, guys.